Okay, so we found general solution when lambda is negative. So next, when lambda is 0, general solution, that's a special case. Right, when lambda is 0.
Then you get p equals 0.
Yeah, so second derivative is 0. What is phi? Okay. Yeah, first derivative will be constant.
Split it out.
Yeah, so then you do one more antiderivative. The function will be a linear function. Yeah, phi is a linear function. So then in that case, phi will be arbitrary linear function, alpha plus beta x. So function of this kind. Okay, if second derivative is 0. And then linear function. So the next one, if lambda is positive, look at this polynomial again. The roots, if this is positive, that means negative, right? Square is negative. You have, yeah, complex roots.
Complex.
Yeah, so the p will be a pair of complex roots because if it's positive, so you take this. Get this, because that's a negative number. You take the square root of negative, so you get a pair of complex roots. That case, we can represent our independent solution phi as a combination of sine cosine, right? So corresponding a pair of complex roots. So cosine square root of lambda x, sine x. So, yeah, if you find two independent solutions, arbitrary combination will be another solution, also a solution. So here's our general solution. We know we have many solutions satisfying the equation, right? So, okay, so for 3 cases, we find general solutions for this second order ODE. But now, we haven't taken into account the boundary conditions yet. So could you decide now if the boundary condition is taken into account, what is the exact form? So we try to determine whether, yeah, so the alpha beta, right?
Will the sine term have an I in the third one or no?
Which one? There's, no, that's just hyperbolical.
The sine one, the third one.
Oh, this one, no, we just use the real valued function.
Okay, real cosine
yeah.
and sine.
Yeah, for
no.
the complex roots, yeah.
Okay, no I's.
No. Yeah. Okay, so what will be the alpha beta if we know the boundary condition? Next is to use this, right? We have general solutions now.
Right.
Determine alpha beta using boundary conditions. Yeah, so let's use boundary condition for each case. We determine specific form, a specific representation for the phi. Then we're done. Yeah, so let's see. If at left it's 0, what happens? You put a 0, right, when x is 0.
So you get phi of 0 equals 0, right?
Yeah, this is gone, right? Because this is a hyperbolic sine 0 is 0. This is gone.
Oh.
And hyperbolic cosine 0 is 1, right? Alpha.
So you get alpha.
Yeah. So that means at alpha, what do we have? Alpha has to be 0. Right? Yeah. Okay, so we got 1. Let's do one more condition, boundary condition. So next so that means this has only one term, right? Because you just put 0, then you know that has to be 0. So alpha is 0. So that means this solution is just this, one term, hyperbolic sine. Hyperbolic sine. Okay, so then put L here. So if we with the other boundary condition, that is with L, we must have 0 as well, right? We have 0 boundary condition. You see, at left and right boundary. So the left boundary implies this is 0. The right boundary implies that has to be 0. Yeah, so then this phi is identically 0. Yeah, we found that in this case, we got a phi that's identically 0. And that's not interesting because either one of them, if it's identically 0, it's a trivial solution, right? So we are not interested in that case. Yeah, so in this case, we get only a trivial solution. From this, you get with boundary condition, with general solution, and phi has to be 0, then so we move on to the next case. So let's decide for the linear case. If left boundary, when x is 0,
Alpha is 0.
alpha has to be 0, yeah. So that means alpha has to be 0. Okay, then next, if alpha is 0, that means phi is this form, right? Just the beta x, just the one term. Beta x, then we make it L. So then let's use the function phi at right boundary. Right boundary has to be what? 0, right? Also the 0 boundary condition. What is beta? Has to be 0 also. So then both will be 0. Then we again get trivial solution. So this case, again we get a trivial solution. That, yeah, so then the U will be trivial solution. Okay, so the way let's move to the third case, see if we can get a non-trivial solution. Third case. So third case, again, you substitute a 0 to, into x, right? Place of x, put a 0. For 0, this is gone. That's a 1, that's an alpha. Yeah, so left boundary condition, 0 boundary condition. So that means the left alpha has to be 0. Yeah, so that means the phi has only one term. That's the term with beta. So beta sine lambda x, right? That is the phi. But when x is L, let's see, it should be also 0. That's the right boundary condition. So for this condition, what's our conclusion? For this case, actually, this is different. Not like the hyperbolic sign. The hyperbolic sign is always non-negative. No, this is this you can imply if this is always 0, then that implies the function has to be 0. It is 0. But this one, this is also it's possible for this part because if this is 0, we'll get again a trivial solution, right? Because already alpha is 0.
So we get n pi, right? Like
yeah, we will, if that's 0, of course you get a trivial solution, but we don't want beta to be 0. So we can require this to be 0, the sign value to be 0. That means as long as this is a multiple of pi. You see, that's a non-negative quantity, right? This square root of lambda. L, lambda is a parameter, so we can make it multiple of pi. So the sign function will be 0 at multiple of pi, right? Because this is non-negative, you see, L is the length of the spatial dimension, and lambda is a real number, it's a positive square root. So that's our requirement. So when lambda, that means when lambda is what value? Divide L squared, yeah. That. So then now it's better we put a subscript because we have multiple values for lambda. So we put a subscript that to show there are multiple possibilities for lambda value, right? So So whenever lambda is one of those numbers in the sequence, then we can have a phi that is non-trivial that will satisfy the boundary condition. This is second order ODE. So we found one case, at least this third case, right, which is non-trivial, and that's also a solution satisfying the boundary value problem. So let's summarize solution of that problem. Yeah, that's a very typical eigenvalue problem, so we better know it very well. So what is the, finally, after we get to this boundary condition, it's called, right, the rigid boundary condition actually in the PDE, if you see that. So this corresponding to that boundary condition, we have this, what's our final solution? Let's give the phi. Depending on lambda, right? Lambda, there are infinite number of possibilities, lambda. So phi corresponding to each lambda n, we will have a phi n, right? So lambda n is that. So they appear in pairs. Whenever given a lambda n, you will get a phi n. Phi sub n is what? So this part, right, because alpha is 0, so it's just the beta times this times x. Square root of lambda, which is square root of this. Correct? So square root of lambda x. Okay, so we have x. So yeah, we can put n here. So we found the solution. And there are infinitely many solutions for that boundary value problem. Okay, so in order to, because for corresponding to each lambda eigenvalue, right, we can, but they're unique up to a constant multiple. That means as long as you don't worry about the constant multiple, then it is a unique solution. Yeah, so we don't have to write that parameter because any multiple of this is still a solution for that problem. Yeah, so for each eigenvalue there's a unique solution. Yeah, unique in the sense that up to constant, right? Okay, so we're done with this part. Now we're ready to look at the h function. So once we get phi and h both, then we can get a solution u as a product. So now we move to the next function h. Next. Yeah, so this one is actually, look at this one with that. They're essentially the same, right? So we don't need to worry about solving it. We have the solution already. So we only focus on this case now. Only focus on that case because the other ones will give you trivial solution. So only for positive lambdas, those positive eigenvalues. Then right now we look at positive, right? Lambda here, we know already it is positive. So that means this is strictly negative. Yeah, so we will look at only that case, third case, for this. Yeah, so what should be solution of this?